Hello everyone! In this lesson, we'll calculate the p-value using the t-distribution, then decide on the hypotheses and compare the p-value for one-tailed and two-tailed tests. And hello again to this lesson, which essentially has two learning objectives. First, following the procedure for a hypothesis test, you should be able to calculate the p-value. Based on this p-value, you should then be able to decide whether or not to reject a null hypothesis. You should also know the effect on statistical power when a one-tailed test is used instead of a two-tailed test. Before starting this chapter, you should look at the lesson on type 1 and type 2 errors, which also explains in more detail what statistical power is. To achieve these learning objectives, this lesson is divided into two chapters. The first chapter uses a case study to test the claim that an alternative adhesive has a higher breaking load. To do this, we calculate the p-value using the t-distribution. In the second chapter, we compare the statistical power of a one-tailed test with a two-tailed one. Let's start with a hypothesis test for a mean using the example of a one-tailed test. Let's look at this assembly as a case study. Some customers claimed a defective product. This product contains the below shown bonded composite joint. This consists of two brackets that are joined by an adhesive. An important feature of this assembly is the breaking load. If the force is too high, the adhesive will fail. The failure mode is a cohesive failure of adhesive A. In the following, we will follow the step-by-step procedure for hypothesis testing shown on the left. Step 1 is to define the problem and identify the parameter of interest. The problem that needs to be solved is that the breaking load needs to be higher. Therefore, the parameter that is examined is the breaking load in Newton. In step 2, we define the null hypothesis. From empirical data from the past, it is assumed that the average breaking load is μ 100 Newton. This is our null hypothesis, since this is the generally accepted status quo. In the formula for the hypotheses, μ is the mean breaking load for adhesive B and μ0 is the mean breaking load for adhesive A from the null hypothesis. In the third step, the alternative hypothesis is formulated. A technician now claims adhesive B has a higher breaking strength μ than adhesive A previously used. This is the alternative hypothesis. So, μ from adhesive B is larger than μ0 from adhesive A. Fourth, we need to define an appropriate test statistic. This means we must determine and calculate a value we can compare to the null hypothesis. For this example, this could be directly the mean breaking load. It shows how closely the observed data agrees with the expected distribution under this statistical test's null hypothesis. However, more standardized test statistics are used, such as the values Z0 and T0 shown here. Such a value is called a test statistic. If the population is normally distributed and the variance of the population is known, the quantile Z0 of the normal distribution is used for the mean values. This is calculated from the mean of the sample, the mean and the standard deviation of the population, and the sample size. In practice, however, the parameters of the population are rarely known. The more common case is that the population's standard deviation is unknown. Then the t-distribution is used for mean values. T0 is then the quantile of the t-distribution. Here's a quick note. Theoretically, adhesive B could also be weaker than adhesive A, but not stronger. If we wanted to test this, we would choose a two-tailed test. But in this example, we are only interested in the effect in one direction and therefore chose a one-tailed test. In the fifth step, we set the rejection criterion for the null hypothesis. So, how strong must the evidence be to reject the null hypothesis? This rejection criterion is set with the value for alpha. Alpha is again the level of significance or error probability. When alpha equals 0.05, there is a 5% chance of falsely rejecting a true null hypothesis. If you want to change alpha, you should know the connection between type 1 and type 2 errors and the statistical power. There is a slightly more detailed lesson on this available. If we determine during our investigation that the test variable is in the critical region and therefore significant, the null hypothesis will be rejected. How do we find the limit to the critical area? There are two ways to do this. The first is using tables for the quantiles of the t-distribution. For a significance level of alpha equal to 0.05 and a degree of freedom of 19, we read a value of 1.729 from the table. The degree of freedom is the number of values minus 1. 1.729 is the limit of the critical region above which a result is considered significant. But there are other ways of doing it. A second possibility to calculate this value is with the help of MS Excel. To do this, use the t.inf function. Here, however, the probability of the left side must be entered, which is 0.954 1 minus alpha. With the same number of degrees of freedom, of 19, the result is also 1.729. Now that we have set up the decision criteria, we have come to the actual p-value calculation. 20 samples were produced with adhesive B and tested. The breaking load values are given in this table here. The t-test assumes that the population from which the sample was taken is normally distributed. Visualizing the values in the histogram with the superimposed normal distribution curve should suffice here as proof. The population appears to be reasonably symmetrical and unimodal, so it has only a single highest value. An average breaking load of 109.15 Newton and a standard deviation of 0.82 Newton are calculated from the 20 measured values. For the previously determined test statistic, we calculate a value of 2.51 for T0. Here you can already see that this value is in the critical region and is therefore significant. Next, we calculate the p-value for this value. Although the p-value could also be approximated using the table used previously for the quantiles of the t-distribution, we want to be more exact here and use MS Excel for this purpose. To do this, we use the t.dist.re function. With the value t0 of 2.51 and the degree of freedom 19, the probability of the p-value is 0.01. As with a comparison of T0 with the critical value, we again get a significant result. A quick reminder. we were willing to accept up to a 5% chance of falsely rejecting a true null hypothesis. With a p-value of only 0.01, we have only a 1% chance of falsely rejecting a true null hypothesis. In other words, the probability of getting a 2.51 or even more extreme value is 1%. The result is significant because the p-value of 0.01 is less than the significance level of 0.05. Finally, considering the overall context, the result must be summarized. So, the null hypothesis was that the mean breaking load of adhesive A was 100 Newton. The alternative hypothesis was that adhesive B has a higher breaking load. So, we formulate the following conclusion. Since the p-value of 0.01 is less than the significance level alpha of 0.05, the null hypothesis is rejected, and we conclude that the mean breaking load with adhesive B is greater than 100 Newton. In this chapter, we compare the statistical power between a one-tailed and a two-tailed test and try to answer the question, which test is better? Let's start with the one-sided test known from our case study. To repeat very briefly, the significance level alpha predicts that a true null hypothesis will be incorrectly rejected. If, as in the previous example, the value of the test statistic is in the critical region, the null hypothesis is rejected. If the alternative hypothesis is true, then the mean of the alternative hypothesis is not equal to the mean of the null hypothesis. As we will see shortly, power is the ability of a statistical test to detect an effect when it actually exists. Our example with adhesive A and B shows that adhesive B has a higher breaking load than adhesive A. The difference between these two breaking loads is the effect size. Similar to the null hypothesis, the values of adhesive B are distributed around the mean. Therefore, the breaking load values of adhesive B will probably also have a different spread and thus a different standard deviation. Analogous to the significance level alpha, beta is the significance level of falsely rejecting a true alternative hypothesis. Thus, 1 minus beta is the probability of detecting an effect that is actually present. This probability is called statistical power. Next, let's look at how beta and power change when alpha stays the same, but we use a two-tailed test. The second alternative hypothesis comes from an employee's claim that the breaking load changed after a process change. So it's supposedly just different. In the first example, the assumption was that this is larger. So if it's different, the breaking load can be higher or lower. We must therefore consider both possibilities and thus carry out a two-tailed test. The significance level alpha is then split into alpha halves for each side. Again, we assume that the alternative hypothesis is true. The mean, the distribution, and the spread should be the same as in the first example. It can be seen that beta is larger than in the one-sided test. The power, the probability 1 minus beta, is therefore smaller. Before we draw any further conclusions from these findings, let's simplify the example again and remove the left-hand side so that the two-tailed test looks like a one-tailed one. What conclusions can we draw now? The statistical power of a hypothesis test depends on several factors, including the size of the effect, the sample size, and the spread. If the error probability alpha is reduced, for example, from 0.05 to 0.025, the critical region for rejecting the null hypothesis becomes narrower, that is, smaller. This can result in fewer cases being identified as significant as the test becomes more demanding. Reducing the significance level alpha can reduce the probability of committing a type 1 error, so having a false positive result. We can see that this is the case in the image below on the right, since the probability of detecting an actual effect decreases as the power of 1 minus beta decreases. So, if we compare the power 1 minus beta at alpha half with the power at alpha, we see that the power at alpha half is smaller. However, reducing the error probability alpha also means a lower statistical power. This increases the risk of a type 2 error. So, having a test that fails to detect a difference or effect when in fact it is there. Conversely, suppose the error probability alpha increases in a hypothesis test from 0.025 to 0.05. In that case, this means that the critical region for rejecting the null hypothesis becomes wider, that is, larger. This makes it easier to reject the null hypothesis because more cases can be identified as significant. This can increase the test's statistical power by reducing the likelihood of accepting the null hypothesis. However, increasing the alpha error rate also increases the risk of committing a type 1 error. This means producing false positive results, since the null hypothesis will be more likely to be incorrectly rejected. For this reason, anyone involved in such statistical studies must make a trade-off between setting the alpha error probability and the associated impact on the power of the test. So, choosing an appropriate testing strategy minimizes the risk of errors while maximizing the power of the test. The well-known value of 0.05 has usually established itself as a good compromise. In the end, it comes down to your expertise to choose the best alpha for your case. So, that was a lot of information. Therefore, I will summarize the 5 most important key messages. Main points from the general procedure for hypothesis tests. Define the test statistic, for example, T0. Where is the critical region? One-sided or two-sided test. Define where the rejection should occur, significance alpha. A test statistic is a number calculated from a statistical test. It shows how closely the observed data matches the expected distribution under that statistical test's null hypothesis. If the significance level alpha is 0.05, the analysis has a 5% chance of a significant outcome when the null hypothesis is correct. Statistical power is the probability of detecting an effect if the alternative hypothesis is correct. And last but not least, a significance level of 0.05 is a good compromise between false positive results and the sensitivity, that is, the power of the test. Use your expert knowledge to select the best alpha for your case. If you found this lesson helpful, please let me know and leave a comment. Thank you for that, take care and see you next time. Bye!